Dear students, in this video we learn some concepts of deadlocks in operating system. Generally, system consists of resources. The resources are like CPU cycles, memory space, I/O devices. Each resource will be having multiple instances. If resource Ri has Wi instances, Rj has Wj instances likewise. Each resource is utilized by the process in the following way. A process requests the resource and uses the resource, then a process releases the resource. When a process accesses the resources in this order, there is a possibility of occurring a deadlock in the system. So what are the conditions for a deadlock to occur? The first condition is mutual exclusion. The mutual exclusion occurs because a process can utilize the resource only one at a time. That is, a process is using a resource when no other process is using the same resource at the same time. Only one process can utilize the resource at a time. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. So that means if a process P1 is holding the resource X and process P2 is holding the resource Y, and each process holding some resources and waiting for other resources held by other processes. That is hold and wait condition. No preemption. If a process is holding some resource, unless otherwise the process voluntarily releases the resource, the process cannot be forced to release the resource. That is called no preemption. That is, a resource can be released only voluntarily by the process holding it. After that, process has accomplished its task. That means until the process completes its resource access, it will not release the resource forcibly. That is the concept of no preemption. Circular wait. Process wait for other resources and forms a cycle. See this in this condition. Assume that there are n processes are there. P0, P1, P2, P3 like that up to Pn. P0 is waiting for the resource held by P1. P1 is waiting for the resource held by P2. P2 is waiting for the resource held by the next process. In that way, Pn minus 1 is waiting for the resource held by Pn. In turn, Pn is waiting for the resource held by Pn minus 1. P3 is waiting for the resource held by P2. P2 is waiting for the resource held by P1. P1 is waiting for the resource held by P2. So each process, without knowing other process status, each process is waiting for the other process to release its resource. In that way, there will be a dependency on each other and there forms a deadlock. There forms a cycle that leads to a deadlock state. So this is one example for circular wait condition. Consider only two processes, for example, P0 and P1. So this is P0 and this is P1. P0 is holding some resource and waiting for P1 resource. P1 is holding some other resource and it is waiting for the resource held by P0. So in that way, P0 is waiting for the resource held by P1. P1 is waiting for the resource held by P0. Likewise, both the processes depend on each other without knowing each other, and this mutual dependency leads to a cycle, and this cycle forms a deadlock. Generally, deadlock is identified in a system by constructing a resource allocation graph. A resource allocation graph consists of V vertices and E number of edges. Okay. So consider there are N number of processes, M number of resources. And there are two types of edges. One is request edge, another one is assignment edge. Request edge is nothing but a process requesting for resource. PI is a process requesting for resource RJ. Assignment edge is nothing but RJ is the resource assigned to process PI. So R to P, that is assigned to assignment edge. So here these are all the symbols used for representing resource allocation graph. Process is represented by using a circle. A resource is represented by using a square. Inside that, the dots indicates the number of instances of the resource. If there is only one instance of the resource, it is represented by a square with a small dot or circle inside that. If two instances of the resources are there, it is represented like this. Two instances. Here 4 instances of the resource is available. So it is represented with a square with 4 instances. So now PI is requesting an instances of one instance of RJ. So therefore this is a request edge. PI is requesting one instance of RJ. Now PI is holding an instance of RJ. See, one resource of one instance of RJ is assigned to PI. So there is a assignment edge. This is a request edge. The first one is a request edge. Second one is an assignment edge. This is request. This is assignment. So assignment edge. In this way, resource allocation graph uses the symbols and edges for representing the allocation of the resources to processes in the system. Example of a resource allocation graph. Let us see the resource allocation graph. Here there are 3 processes are there and 4 resources are there. So R1 is having one instance of the resource, R3 is also a single instance, R2 is 2 instances of the resource, and R4 is having 3 instances of the resource. Now P1 is requesting R1, but R1 is assigned to P2. P2 is requesting R3, but R3 is assigned to P3. R2, there are 2 instances of the resource is there. One instance of R2 is assigned to P1, another instance of resource R2 is assigned to P2. R4, 3 instances of the resource, but no process is being allocated by this particular resource. Now whether there is a deadlock in the system or not. How do you find? So we will check for any cycles or dependency in the system. So let us check for the dependency. In order for P1 to complete its execution, it requires R1, but R1 is not free. R1 is allocated to P2. In order to execute P2, P2 requires R3, but R3 is allocated to P3. So what about P3? P3 is required only R3. R3 is allocated to P3. P3 does not require any other resources. So P3 will go for execution and it will complete the execution and it release the resource R3. So R3 after release, R3 is allocated to P2. So P2 will go for execution. So after P2 gets execution, it will release R3 as well as R1 as well as R2. So these 3 resources are released by P2. Then coming to P1, P1 is waiting for R1. R1 is released by P2. So therefore R1 after assigned to P1, P1 will go for execution and then P1 also will complete. So therefore this is a safe state. So all the processes are completing its execution by utilizing the resources available in the system. So therefore there is no deadlock, and this is how we can find out whether there is a deadlock in the system or not by constructing the resource allocation graph like this. Now let us check one more example for resource allocation graph usage to find the deadlock state. So here again P1 is waiting for R1, R1 is allocated to P2, P2 is waiting for R3, R3 is allocated to P3, P3 is waiting for R2, but R2, two instances of R2 are available. One instance is allocated to P1, another instance is allocated to P2. So this is the state of the system. Now P1 wants to execute. So in order for P1 to execute, it requires R1, but R1 is not available. So P1 will be waiting. P2 wants to go for execution, but it requires R3, but R3 is not free, it is allocated to P3. So P2 will also be in waiting state for R3. Coming to P3, P3 is having R3, but P3 require R2 also, but R2 resources are not free. So P3 will also enter into a waiting state. Like that, P1, P2, P3, all the three processes will be in the waiting state. So waiting for one or other resource to available, but that condition will not occur because every process is waiting for other process without knowing each other. So therefore there forms a deadlock state, there forms a cycle. So here there are two cycles in this resource allocation graph. One cycle is P2 to P3, that is R2 P2, R3 P3 R2. So this is one cycle. Another cycle is this way. So here this is another cycle. So this again forms a deadlock. So likewise there are two cycles are there in this system. So therefore there is a deadlock in the system. Now we will see one more resource allocation, whether there is a deadlock or not. Let us check it. P1 is waiting for R1. There are two instances of R1. One instance of R1 is allocated to P2, another instance of R1 is allocated to P3. P3 is waiting for R2. R2, one instance is allocated to P1, another instance is allocated to P4. Now let us check P1 whether it will continue its execution or not. P1 is waiting for R1, but R1 is not free. R1 is allocated to P2 and P3. So P2 wants to execute. So P2 will go for execution because it is not having any other dependency. Whatever resource it requires R1 that is available, so P2 will go for execution. So P2 after completing its execution, it will release the resource. So once R1 is released, so the one instance of R1 will become free and it will be assigned to P1. So P1 will go for execution. So P1 already R2 is having. So R1 also P1 will get. So P1 will go for execution. Once P1 complete its execution, then P1 will release R1. So once R1 is released, then next process which is waiting for what is the next process? P3. P3 is waiting. So P3 will get R2 because P1 is completing its execution. So therefore R2 is released. So once R2 is released, P3 also will go for execution. Otherwise, if P4 is another process which is being executed because R2 is there for P4, P4 does not require any other resources. Therefore, P4 also completes its execution. Either P1 or P4, any one of these processes completes its execution, R2 will get released. Once R2 is released, P3 will go for execution. In that way, all the processes will complete their execution one after the another in some order, such that there is a cycle in this graph, but there is no deadlock in the system. But there is one more point to be remembered. If multiple instances of the resource are available, even if there is a cycle, there may not be a deadlock in the system. But if only single instance of the resource is available, consider we have only single instance. So this is one process waiting for this resource R1. R1 is a single instance. It is allocated to P2. So here R2 also single instance. P2 is waiting for R2, but R2 is assigned to P1. Now you see that here single instance is there. P1 is waiting for R1, R1 is allocated to P2. P2 is waiting for R2, R2 is allocated to P1. That forms a cycle. So either P1 or P2 should complete its execution, but they cannot go for execution because they are waiting for one more resource availability. So this forms a cycle, and this leads to a deadlock state. For example, if the same situation, if two instances of the resources are available, either R1 or R2, so one of the process will go for execution and says, and then there will not be a deadlock. So this is how, if multiple instances of the resources are available, even if there is a cycle, there may not be a deadlock. But if only single instance of the resource is available, and if there is a cycle, then there will be a definite deadlock in the system. This is what we have to remember from this example. How do we handle the deadlock? There are three methods for handling the deadlock. One is deadlock prevention, deadlock avoidance. Third method is deadlock detection and recovery. Coming to deadlock prevention. So as there is a say that prevention is better than cure. So here we see that there should not be a deadlock in the system by availing some prevention mechanisms. What are the prevention mechanisms? So here the conditions for the deadlock is mutual exclusion, no preemption, hold and wait, circular wait. These are the conditions for the deadlock. We are going to relax these conditions so that these conditions will not lead to a deadlock state. That is the idea behind the deadlock prevention. Coming to mutual exclusion. Mutual exclusion, we can relax the mutual exclusion in deadlock prevention. So only the mutual exclusion is followed for non-shareable resources only. If it is a shareable resource, mutual exclusion need not be followed. What is mutual exclusion? If one process is using a resource, other process should wait until the first process releases the resource. That is called as mutual exclusion. So only one process should use the resource at a time. That means critical section. When one process is in the critical section, no other process is allowed to enter into the critical section. That is the meaning of mutual exclusion. Similarly, here in order to prevent the deadlock, the mutual exclusion condition can be eliminated for shareable resources. The mutual exclusion condition must be applicable only for the non-shareable resource. What is meant by a shareable resource? A read-only file is a shareable resource. For example, if there is a read-only file, if any number of processes make use of that read-only file, it is not going to be affected. So any number of processes can make use of the read-only file at a time. So this is shareable resource. Read-only file is a shareable resource. Coming to non-shareable resource, CPU is a non-shareable resource. If one process is using the CPU, unless otherwise that process completes its execution, no other process can be assigned. No other process will get CPU access. So that is, CPU is a non-shareable resource. So likewise, we can divide the resources into shareable resources and non-shareable resource. If there is a shareable resource, we can directly assign to the requesting process without need to check whether that process is under use by the another process or not. Because they are shareable, we can directly assign them without need to check. But if it is a non-shareable resource, if it is free only, we can allocate them. Otherwise, the process can be made wait if it is non-shareable resource. That is the relaxation given for shareable resources in the mutual exclusion. Coming to hold and wait. A process hold and wait must guarantee that whenever a process requests a resource, it does not hold any other resource. That means every process should request all its resources before its execution, or allow process to request resources only when it has none resources allocated to it. So this is a condition for hold and wait. Because of this, there will be a low resource utilization, and starvation is also possible because a process is waiting for some of the resources, and if any of the resources are not available, it has to wait for long duration of time until all the resources are available. Then only it can get allocated to that process. If some resources are available, if few resources are available, few resources are not available, then a process cannot hold those few resources and wait for few more resources. The condition is here either the process should not have any resource with it, or a process should request all the resources at the beginning itself. If all are available only, then it is allocated to the process. So that is the requirement for hold and wait. No preemption. If a process that is holding some resources requesting another resource that cannot be immediately granted, then all resources currently being held are released. For example, P0 is one process, P1 is another process. P0 is holding X, P1 is holding Y. P0 requires Z. Okay, but Z is not available. Z is not available. It is held by some other process, P3. Suppose P0 requires Z, but it is held by P3. So then what is happened according to no preemption? P0 should release X because P3 is holding Z. It cannot be immediately granted to P0. So therefore, P0 cannot request for Z. It can request Z only after releasing X. Then again P0 has to request X and Z together. That is no preemption. So when P0 releases this X, then X will be allocated to some process that is waiting for X. Then when do this P0 will start its execution means when the P0 gets both X and Z availability, then only P0 will go for execution. That is about no preemption. No preemption condition relaxation. What is general no preemption condition? No preemption says that no process is forcibly terminated. That is no preemption. But here we are relaxing this no preemption condition. If a process is holding some resource waiting for some other resource, then the process should release the resources. It should ask all the resources together afresh. That is the meaning of no preemption. Coming to circular wait. So here a total ordering of all the resources are maintained, and every process should request the resources only in this order, in the increasing order of their enumeration. For example, in this case, there are some processes P0, P1, P2, P3 like that. They want to request the resources, and there are some resources X, Y, Z or something like that. There are some resources in the system. Based on every resource will be given some priority. It can be considered like some priority number or order of requesting the resource. Every resource will be given some order of request. So that means the resources are given some number 1, 2, 3, 4, 5, 6 like that. The resources are given some number. Suppose if a process requests a resource whose priority number or enumeration number is 1, then it can ask a process with resource in increasing order of their enumeration. 1, 2, 3, 4 like that only. For example, if a process P1 requested the resource whose enumeration order number is 3, then it cannot ask the resources 1 and 2. It should ask the resources only whose enumeration order number is after 3. So, in the increasing order of enumeration only, the resources can be requested by the process. Suppose if the process unknowingly requested a resource whose enumeration order is, for example, 3. P1 requested 3. After some time, P1 found that it required resource 2 also or 1 also. Then what P1 has to do means, whatever resources it is holding currently from 3, it has to release all these resources. Again, it has to start from the starting enumeration number from 1, 2, 3, 4 like that. In this order only, the processes can request the resources for access. If they are available, they will be assigned to the process and they will be go for execution. If they are not available, then the process is made wait for the availability of that resource. Once they are available, it will get access to that particular resource. So that is how, for example, process P2 asked P resource with number 4. Then it can go from 4 only. 4, 5, 6, 7 like that. It cannot ask the resources which are present before 4. So this is the called as order of enumeration. This type of ordering is maintained for the resources which are available in the system, and the processes can request the resources only in this order such that there will not be a deadlock. So in this way, deadlock is prevented by following some techniques in the system. Coming to deadlock avoidance. Deadlock avoidance is also one of the technique used for handling the deadlocks in the system. Here there are n number of processes, m number of resources will be there. So when we are allocating a process with some resources, the system will check that whether the system will be in the safe state or unsafe state. If the system is in safe state, that means the resources will be allocated to that process. If the system enters into unsafe state when those resources are allocated, then system will not allow allocation of those resources to that particular process. So therefore, deadlock avoidance is ensured by verifying the state of the system before allocating the resources to a process. If a process, whatever resources are requested after allocation, if the system is in safe state, these resources are allocated. If the system enters into an unsafe state, then the system will not allocate those resources to that particular process. This is how deadlock is avoided. In order to handle the deadlock avoidance, we have one algorithm that is called as the Banker's algorithm. In next video, we will see how this Banker's algorithm is used for avoiding the deadlock in a system. So, what is this safe state and unsafe state says? If the system is in safe state, it means that there is no deadlock. If system is in unsafe state, there is a deadlock. Deadlock avoidance ensures that a system will never enter an unsafe state. Thank you for watching this video.